to projects. In this video, we are going to explain about the project that is XAI, evaluating black box explainable AI frameworks for network intrusion detection. Before getting into the execution, first let us understand what is the project about. So let's talk a bit about growing challenges in cybersecurity. If you think about it, that we are surrounded by technology all the time, whether it is in our personal devices, businesses, or even national infrastructure. With all this data being transferred every second, it is only natural that cybercriminals are constantly looking for ways to exploit weaknesses. The problem is these attacks are becoming more sophisticated and they are happening faster than we keep up with. This is why there is an urgent push to develop systems that can only detect these attacks but also respond quickly and efficiently. So here where intrusion detection systems comes into the place. So these are used for detecting and spotting the malicious activity in the network. So we do have some methods that are traditional methods, which are human intuition and also signature of known attacks. But as variety of attacks grows, these approaches just isn't enough. So we started turning to AI. So we have started turning to the AI based models, that is machine learning based models. Because it can analyze massive amount of data, they can spot patterns and also predict potential threats. But here, the tricky part is while AI is great at identifying anomalies and potential risks, it is not always clear why it makes a particular decision. It is like having a friend who tells you something wrong, but when you ask them how they have figured it out, they just say shrug and say that I just know. So this AI intrusion detection systems, they are like the black boxes where they don't have the clear picture that why they have taken that particular decision. So in cybersecurity, it isn't ideal because you need to understand that reasoning behind the alerts and decisions. AI makes especially when dealing with something as critical as potential breach. Imagine being a security analyst and receiving an alert from an AI system about a possible intrusion. It is important to understand why the AI flagged it so you can make informed decisions on what to do next rather than just blindly trusting it. That is where the concept comes explainable AI. It is all about making these AI models more transparent and interpretable so we can see what the factors influence their decisions. This helps to ensure that decisions are not just accurate but also understandable and trustworthy. By providing insights into how decisions are made, XAI ensures the security analyst can understand and trust the system's logic. This transparency is essential for real world deployment as it allows analysts to confidently act on alerts knowing they can validate the system's reasoning. With XAI's ideas that is intrusion detection system, this becomes not only more reliable but also more actionable, making it a critical component in effective network security. So the system that we're talking all about is detecting and classifying network intrusions. So it is like having a watchful eye on constantly scanning network traffic for anything suspicious. So here we consider three data sets which are NSL KDD CICIDs 2017 and SIMARGL 2021 data sets. So these data sets are a collection of past network traffic, both normal and with known attack patterns. By using this data, the system learns to distinguish between what is regular network traffic and what might be an attack, like denial of service attack or a brute force attempt. So to make these decisions, that is to detect the intrusions, here we are incorporating multiple bunch of machine learning algorithms that are random forest, deep neural network, support vector machine, and light GBM, which are more advanced tools. Each of these models works on the data, process it, and helps to identify whether the traffic is normal or if something malicious is going on. This approach makes the system more accurate because it is not just relying on one type of the model, but rather a group of them that can catch different kinds of threats in their own way. So we will be evaluating all of them and we will be selecting the best performing model. As the system is all about not just detecting intrusions but also helping people understand how it makes decisions, this is where explainable AI comes into the picture. So it is like trying to explain why you made a certain choice to someone else so they can trust your reasoning. So the system uses two methods, that is LIME and SHARP. LIME is of local interpretable model agnostic explanation. It is a technique that looks at individual predictions and breaks them down. It shows which features or pieces of the information has the biggest impact on the decision. For example, let's say the system flags something a potential brute force attack. Lime would show you why that decision was made. Was this the number of failed login attempts? Or maybe IP addresses involved? On the other hand, SHAP, that is SHAP, takes a broader approach. Instead of focusing on one decision at a time, SHAP shows you a global view of features that are most important across the entire dataset. It does this by generating summary plots that visually represent feature importance, helping you see the overall patterns. So, by using Lime and SHAP, the system not only makes the predictions but also gives you a clear explanation of why those predictions were made. This makes the system more trustworthy and interpretable, which is crucial when it comes to network security. After all, if a security analyst can understand the reasoning behind the system's decisions, they can act on them with more confidence. So, this is about the proposed system. So, to further improve the accuracy of the project, we are incorporating voting classifier, which is an ensemble technique as an extension. So, this combines predictions from multiple individual models. It is like asking several experts for their opinion, and then we take the majority vote as the final decision. This way, we get a more robust and accurate prediction because it is based on combined knowledge for several models. On top of that, we have built front end using Flask framework. So, this makes the system user friendly, allowing people to interact with it easily. The interface includes also a login and registration setup that uses the user authentication mechanism. This ensures that only authorized users can access the system, which is crucial for security. In simple terms, this extension makes the system both more accurate and also easier for users to test and interact within a secure way. And moving on to the implementation part, to implement this project, we have followed the steps mentioned in the flow of work. So these are the steps followed. Let us understand them. First, we have imported all the required necessary Python libraries and packages required for data handling, model building, visualization, evaluation. Then comes exploring the dataset part. So here we analyze the datasets that are SIMARGL, NSLKDD, and CIC-IDS 2017 datasets to understand their structure, features, and types of intrusions they contain. This helps to know what we are working with and how to prepare the data. Then comes data processing. So here we remove any repeated rows in the dataset. So here we remove repeated rows, that is a duplicate rows in the dataset to avoid bias. Then unnecessary columns are dropped and we normalized we normalize the data set or we scale the data set, ensuring that all features are on a compatible scale for better performance. Then we do visualization. Visual representations of the data are created to better understand patterns, distributions, and also relationship between features. And we convert all the categorical variables into numerical variables. After that, we select the most important features from the data set to reduce the dimensionality and improve the model efficiency. Then we split the data into train and test, where training set is used to train the model and testing set is used to evaluate the model. Then comes building the model with Lime. So your machine learning models are initiated and Lime, that is local interpretable model agnostic explanations, is used to explain individual predictions made by the each model. And we train the model with the training data where it learns patterns and relationship between features and the target variable. And we evaluate all of them using accuracy, precision, recall, and FN score, and we compare through them graphs. Then comes front end part. So a simple user interface is developed using Flask, allows users to interact with the system. It also includes a registration and login setup backed by an SQLite database for user authentication. And in the front end users, they will be able to provide the input feature values that is related to network traffic features in the front end. That will be pre-processed at the back end. It will be fed with the trained model. Finally, outcome will be displayed to the front end of the application. So this is how we have implemented. And now coming to the algorithms used, these are the algorithms used in the project. Each algorithm is combined with the Lime for explaining the predictions of model made. So here we have incorporated DNN, AdaBoost, Light GBM, KNN, MLP, random forest, support vector machine, extension model that is boosted decision tree with the bagging random forest. This is the voting classifier model where it combines boosted decision tree and bagging random forest. And to implement this project, we need basic requirements which are hardware and software. Coming to hardware, we need operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Coming to software, we need application of Anaconda, primary language of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, and front-end technologies are HTML, CSS, JavaScript, and Bootstrap 4. This is all about the overview of the project. Now let us execute. So open the code folder that contains source code files. So let's open the code folder. These are the source code files of the code folder of the project. Let us understand each of them. How will they be used in this project? So here in this folder and this folder, we have the datasets that are used in the project. So in CIC IDs 2017, these are the files we have, and NSLKD, these are the files, and SIMARGL, this is the dataset that we have. So we will be pre-processing all these three datasets. All these three will be pre-processed as mentioned. So here is the CIC, this is the dataset, and this is the processed file of CIC IDs 2017. So we will be training this data to predict the intrusions. So this is the target column. So this we will be predicting in the front end. Close this. Similarly, here we have NSL process data and SIMARG process data also. And here in this model folder, we have the algorithm information that is stored in .h5 files, numpy files, and pickle files, and they will be loaded into the project code during runtime of the application. And here in the sample folder, we have the sample files that we will be using in the front end for predicting the intrusions. And this is static file. In this file, we have CSS, JavaScript, and Bootstrap files which are important for the visual appeal. Then comes the templates folder. This folder contains all the HTML pages used in this project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. And this is the app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in HTML templates. So here we have three Jupyter Notebook files. So here we have three Jupyter Notebook files. These files contain the combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, which makes it a popular choice for the data science. So here we have three notebook files because in this Jupyter Notebook file, we will be loading CIC process data, and then we will be training the models on CIC IDs. Similarly, NSLKDD and also SIMARGAL dataset also. Individually, we will be predicting intrusions on three different datasets. And this is the signup.db file. This file is a database file which is used to store the user information. This is all about the code folder. Now let us execute. So copy the path of the code folder from the address bar of the file explorer. I've copied the path. Now open Anaconda prompt. It is open. Give the command cd, give the space, paste the copied path, and now click on enter. Here, if you observe, current directory is changed to the code folders path. Now compile app.py file. So give the command python space app.py and now click on enter. This command will execute Python script and perform a runtime check for any syntax errors or logical issues. And after running the app.py file, Flask framework will host the application locally at the default address, which is the local host and the port unless configured differently. So copy this local link provided by the Flask framework and paste it into any web browser. I'm copying the link. I prefer Google Chrome, so I will paste it in that. Paste the link here, click on enter. This is the web page of the project, which is displayed in the browser, and this is developed using Flask framework. So we need to sign up first. Click on sign up, register, and enter all the registration details if you are registering newly. I have already registered, so I will directly sign in. Click on sign in. And here we are supposed to provide username and the password. So give your username and the password. Now click on login. We have logged in successfully and we are redirected to prediction page of the project. As we are considering three datasets that are SIMAR, GAL, NSL, KDD, and CIC ideas, we will be detecting intrusions using all the three datasets. So first, let's do detection using SIMAR, GAL 2021 dataset. So click on that. So these are the input features need to be given as the input. Based on that only, we will be getting the prediction. So the first one we have is the flow duration microseconds. This refers to the duration of the network flow in microseconds. And here we have flow duration milliseconds. Similar to the previous input, but this one measures the flow duration in milliseconds. It helps to understand the duration of a network flow with a coarser time scale. Then we have in bytes. This represents the total number of bytes received by the system or device in a network flow. It helps to quantify the amount of incoming data during a specific flow. Then we have L4 DST port. This is the layer 4, that is transportation layer, Destination port number, it specifies the port on the receiving side of the network flow, typically used to identify the service or application being accessed. Then we have L4 SRC port. This is the layer 4 source port number. It indicates port on sending side of network flow, which is typically corresponds to the service or application initiating the connection. Then we have out bytes. So this refers to the total number of bytes sent out by the system or device in a network flow. It measures the amount of data transmitted during the flow. Coming to protocol, this represents the protocol used in the network flow, that is TCP, UDP, ICMP, etc. It indicates how data is transmitted across the network, helping to identify the type of communication. TCP flags. These are the flags set in the TCP header to control the flow of data in a TCP connection. Common flags include SYN, ACK, FIN, RST, etc., which helps to manage connection establishment, maintenance, and termination. Then comes TCP win maxin. So this indicates the maximum size of TCP received window on the incoming side. It helps to control how much data is being sent before waiting for an acknowledgement. Then we have TCP win minin. So this represents the minimum size of TCP received window on the incoming side, which can indicate how much data the system is ready to receive. The last parameter is the TCP win MSS in. This is the maximum segment size, that is MSS for incoming data. It defines the largest amount of data that can be received in a single TCP segment, excluding the TCP header. So this is all about the parameters. Now we are supposed to enter. So open the sample file of the same data set. So this is the sample file. So let's apply filter to the target label. So here total we have two classes. So let's apply filter to the class 0 and enter the values. So let's try with this case where flow duration microseconds is 34877 and milliseconds is 34 milliseconds. In bytes value is 111, L4 is 53, and L4 SRC port is 42719. 220 are the out bytes. Protocol is 17. 0 is TCP flags. TCP win maxin is also 0. And all the next values are 0. Now click on predict. So this given input, it will be pre-processed at the backend and then train model will be giving us a prediction. So here we got the prediction that normal flow, which means there is no attack detected in the given flow data. So here there is no attack. Let's try with class 1. Apply filter to class 1. So let's give this case, click on prediction under SIMARGL 2021 and flow duration is 0, milliseconds is 0, in bytes value are 44 and L4 SRC bytes are 59166. L4 SRC port are 49982. 0 is out bytes. Protocol is 6. TCP flags are 2. TCP win maxin is 1024. Min in is 1024. MSSN is 1460. Now click on predict. So here we got the prediction that SYN scan aggressive. That means there is an attack there. So that is SYN scan aggressive. So here we got the prediction that there is an attack detected. So we are done with this prediction of SIMARGL. Similarly, you can predict with a number of test cases for the same data set. Now let's check with the NSL KDD. So here are the inputs need to be given for this NSL KDD data set. Let us understand them. The first parameter we have is service. So this refers to the specific application or service being accessed in the network flow, such as HTTP, FTP, SSH, etc. It helps to identify the type of service being used during the flow. Then we have flag. This represents the status flags in the network connection, indicating the state of the connection. It helps to identify the connection behavior, such as whether a session is established or terminated, or if there is a reset. Then we have source bytes. This represents the total number of bytes sent from the source in the network flow, that is sender. It measures the amount of data transmitted from the source to the destination during the flow. Then we have destination bytes. This represent the total number of bytes sent to the destination, that is the receiver, in a network flow. This measures the amount of data transmitted from the source to the destination during the flow. Logged in. This indicates whether a user is logged into the system or not during the flow, typically used to distinguish between authenticated and unauthenticated sessions, helping to detect unauthorized access. Count. So this refers to the total number of events within a specific time period. It helps to track the volume of activity, which can be useful for anomaly detection. Same SRV rate. So this represents the rate at which the same service is accessed by the source. It indicates how frequently the source interacts with the same service, which may help to identify patterns such as repeated access to a specific service. Then we have different service rate. So this measures the rate at which different services are accessed by the source. A high rate of accessing different services in short time might indicate scanning behavior or other suspicious activity. Then we have destination host service count. So this indicates the count of service accessed by the destination host. It helps to identify how much different services the destination has been interacting with during the flow, which could highlight unusual or unauthorized access. Then we have destination host different SRV rate. So this measures the rate at which the destination host access different services. A high rate could indicate potential attacks such as denial of service attack, where a target host is overwhelmed by a variety of service requests. So this is all about the parameters. Now let's open the sample file of this data set, that is an SLKDD. Open the sample file. So these are the samples we have here. Let's apply filter to the target class. So let's apply. Totally here we have 5 classes. So let's apply filter to class 0. So let's try giving the first case where service value is 43, flag is 1, SRC bytes are 0, destination bytes are 0, logged in value is 0, and count is 139. 0.12 is the same SRV port, SRV rate. Different SRV is 0.06. Destination host is 15. And 0.07 is the destination host SRV rate. And then now click on predict. So here we got the prediction that attack is detected and that attack type is DOS attack. So here DOS attack has been detected. Now let's check with the class 1. So let's apply this case. Click on prediction, click on NSLKDD. Here service value is 39 and the next value is 4. Flag is 4. 1 is source bytes, destination bytes are 0. Logged in value is 0. Count is 2. 1 is same SRV rate and 0 is a different SRV rate. Destination host rate is 2 and 0.63 is the destination host different SRV. Now click on predict. So here we got the prediction that there is no attack and it is normal. So here normal is detected. That means there is no attack. Now let's apply filter to the class 2. So let's try with this case. Click on prediction, click on NSLKDD. So here service is 17, flag is 9, source bytes are 1225, destination bytes are 2449, logged in value is 1, count is 1, same SRV is 1, different SRV is 0, destination host SRV count is 91, and different host is 0.02. Now click on predict. And here we got the prediction that there is an attack and that attack type is probe attack. So your attack is detected and it is probe attack. Let's try with the third class label. Click on OK. So let's try with this case. Click on prediction, click on NSLKDD. So service is 17. 9 is the flag. Source bytes are 230. Destination bytes are 644. Logged in value is 1. Count is 1. Same SRV rate is 1. Different SRV is 0. Destination host SRV is 1. And 0.75 is the different SRV rate. Click on predict. So here we got the prediction that there is an attack and that attack type is R12 attack. So here class 4 refers to the class 3 refers to the R12 attack. Now let's check with the last class label of the data set. Click on OK. So let's try with this case. Click on prediction, click on NSLKDD. And here service is 21, flag is 9, source bytes are 356, that is 356, destination bytes are 7095, logged in value is 1, count is 19, same SRV is 0, different SRV is 225, and the next value, we have entered something wrong. Let's recheck again. So this is the case that we are entering, right? So the first value should be 29, 9, 356, 7095, 119, and the next same SRV rate is 1. And the next different SRV rate is 0. And then destination host SRV rate is 255. And the last one is 0. Now click on predict. So we have completed with all the cases. So here we got the prediction that there is an attack detected and that attack type is U2R attack. So here U2R attack has been detected. We have completed with the NSL KDD also. Let's try predicting CICIDS 2017. So click on that. So here also we have parameters that are need to be given as the input. Let us understand each of them. How will they be used in this project? So the first one we have is the flow duration. This represents the total duration of a network flow, typically measured in seconds or microseconds. Then we have forward packet length total. So this is the total amount of data being transmitted in the forward direction, that is from source to destination. Then we have backward packet length total. This represents the total amount of data that is in bytes transmitted in backward direction from destination to source during the flow. And then we have forward packet length max. So this is the maximum packet size in bytes observed in the forward direction during the flow. It indicates largest packet sent from the source to the destination. Then we have forward packet length mean. So this is the average packet size in bytes in the forward direction. It is calculated by dividing the total forward packet length by number of forward packets. Then we have flow IAT max. This refers to the maximum inter-arrival time between two consecutive packets in the flow. A high value could indicate delays between packets or irregular traffic patterns which might suggest issues or attacks. Then we have forward IAT mean. So this indicates the average inter-arrival time of packets in the forward direction. It measures the time between consecutive packets sent from source to destination. Then we have forward IAT max. So this indicates the maximum inter-arrival time between consecutive packets in the forward direction. It is useful for identifying delays or gaps in a packet transmission. Then we have forward header length. This is the total length in bytes of the headers in the forward packets and it includes information needed to route and manage the flow. Then we have backward header length. So this is the total length that is in the bytes of the header in the backward packets. It represents the routing and management information for packets traveling from destination to the source. Then we have backward packets. This is the rate, that is packets per second, of backward packets being transmitted. It helps to understand the rate at which traffic is following in the opposite direction. Then we have packet length maximum. So this is the size of the largest packet in the flow regardless of a direction, forward or backward. It gives insights into the maximum data chunk sent in a single direction. Then we have packet length mean. This is the average size of the packets in the flow calculated by dividing the total length of packets by the number of packets. Then we have packet length standard deviation. So this stands for standard deviation of packet lengths. A high standard deviation suggests there is a significant variation in the packet sizes which could indicate irregular traffic patterns. Then we have packet length variance. This is the variance of packet lengths measuring the spread of distribution of the packet sizes. High variance could point to inconsistent or irregular traffic behavior. Then we have average packet size. This is the average type of all packets in the flow. It provides an overview of the typical data volume per second. Then we have average forward segment size. This is the average size of the segments in the forward direction. It is typically useful for analyzing efficient of data transmission in the forward direction. Then we have subflow forward bytes. This refers to the total number of bytes transmitted in the forward direction within a subflow. Then we have initial backward win bytes. This is initial number of backward window bytes used in the flow. It indicates the available buffer size of the backward flow during initial stages of communication. So this is all about the parameters. Now let us enter them. For that, let's open the sample case. So here are the parameters. Let's apply filter. So total we have 7 class labels. Let's apply filter to class 0. Click on OK. And let's apply. Let's upload the parameters. Let's give the input. So let's try with this case. So here the flow duration is 23024 and total forward packet length is also 0. The next three values are also 0. And then we have flow IIT max, that is 23024, and IIT mean is 0. The next value is 0. 32 is the forward header length and the backward header length is also 32. And then we have backward packets that are 43.43294 and length max. The next all values are 0 up to subflow bytes. So let's give the values as 0. And the last value is 939. Now click on predict. So here we got the prediction that no attack is detected and it is benign. So here we got the prediction that benign. That means there is no attack. Now let's check with the class 1. So apply filter to the class 1. So you're supposed to give the inputs. Click on prediction. Click on CICID is 2017 and flow duration is 227. Forward packet length is 14. Backward packet lengths are 0. Forward packet length is 14. 7 is forward packet length mean. 139 is flow IIT max. 227 is IIT mean. IIT max is also 227. 64 is header length and 20 is backward header length. Backward packets are 4405.286. Packet length max is 14. 7 is the packet length mean. Packet length standard deviation is 8.082904. And variance is 65.333. And then average packet size is 9.333. And average forward segment size is 7. Subflow forward bytes are 14. And initial win bytes are 0. Now click on predict. So here we got the prediction that attack is detected and that attack type is bot attack. So your bot attack has been detected. Now let's check with the class 2. So apply filter to class 2. Click on OK. And now let's try giving this case as the input. Click on prediction. Click on CICIDS 2017. Here flow duration is 57. Forward packet length total is 0 and the next four values are also 0. And then IIT max is 57. IIT mean is 0. Max is 0. And the next value is 32, that is header length. Then we have header length that is also 32, backward header length. Then we have backward packets that is 17543.860 and all the next values are 0 up to the last one. So let's give zeros up to last one. And the last one is 1176. Now click on predict. So here we got the prediction that attack is detected and that attack is nothing but brute force attack. So here brute force attack has been detected. Now let's apply filter to the class 3. Click on OK. So let's try with this case. Click on prediction. Click on CICIDS 2017. So here I have entered all the parameters. Now let's click on predict. So here we got the prediction that there is an attack and that attack type is DDoS attack has been detected. So here DDoS attack is detected. Now let's try with the class 4. So apply filter to the class 4. Click on OK. Let's enter this case. Click on prediction. Click on CICIDS 2017. So I have entered all the inputs of the first case. Now click on predict. Here we got the prediction that there is an attack detected and the attack is DOS attack. So here attack is DOS attack. Now let's try predicting class 5. Click on OK. So let us enter this case. Click on prediction. Click on CICIDS 2017. So the flow duration is 740. Packet lengths are 8. Backward packet length is 2. And packet length max is 6. mean is 4, 577 is the IIT max, 740 is the IIT mean, and the next value 740 is the IIT max, and the next value is forward header length, that is 44, 24. Backward packet length is 1351.3513. Length max is 6, and packet length mean is 3. 2 is a standard deviation. 4, the next three values are 4, so give the values as 4. And the subflow bytes are also 4. Now click on, sorry, we are supposed to give 8. So click on predict. We have entered it wrongly, so let's enter it again. Click on CIC ideas. So the first value, that is flow duration, is 740. Packet length is 8, 2, 6, 4, 577, 740, 740, 44, 24. Then backward packets are 1351.3513, and packet length is 6, 3, 2, 4. The next three values are 4, and then the next value is 8, and the last value is 29200. Now click on predict. So here we got the prediction that there is attack detected and the attack type is port scan attack. So here port scan attack has been detected. Now let's check with the last case. Click on OK. So we have to give this case. Click on prediction, click on CIC IDs 2017. So copy the flow duration, paste it, and then the next 4 values are 0. So give the zeros of next 4. And then we're supposed to give the flow IIT max. So copy the flow IIT max, that is 5989646. Then flow forward IIT mean. Then forward IIT max, copy it, paste it. Then forward header length, that is 104. Backward header length is 40. Backward packets is 0.166. Let's copy it and paste it. The next values are 0 up to the last second one. So let's give zeros. And the last one is initial 1 bytes. So paste it. Now click on predict. So here we got the prediction that attack is detected and that attack type is web attack. So your web attack has been detected. So this is how you need to execute. Now let's check with the graphs. Click on graph. So here the first graph we have is a sample outcome graph of the SIMARGL dataset. So this is the first sample outcome graph. This shows the distribution of the target class of the project. Here on x-axis we have the target class and on y-axis we have the count of each attack. That is the normal flow and the SYN scan aggressive. And here we have correlation matrix, which shows the correlation between variables. And this is the accuracy comparison graph. Here on x-axis, we have accuracy score, and on y-axis, we have all the algorithms that are trained for predicting the intrusion. And here we have precision score comparison graph. This is the recall score, and this is FN score. And here we have NSL KDD sample outcome. So here on x-axis, we have all the attacks of NSL KDD dataset, and on y-axis, we have count of each attack. And here is correlation matrix, accuracy, precision, recall, FN score. And here we have sample outcome of CIC IDS 2017 dataset. So these are the attacks. And here on y-axis, we have count of each attack. This is the correlation matrix. This is the accuracy comparison graph. This is the precision score, recall score, and the F1 score. Now click on logout. In this, just by giving inputs to the application based on the given input, application will be predicting whether there is an attack or not. If there is attack, it will detect which type of attack it is. If there is no attack, it will show that there is no attack. It is normal or either benign. So this is all about the project.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.